Let's build a power series for f of x. So we got to kind of think, first of all, what do we know about f of x? So in general, we have this power series that is going to have some coefficient a, x to the power 0, plus a1 times x minus c to the power 1, plus a2, x minus c to the power 2, etc., all the way to infinity. So what do we know about this f of x series? Well, if we plug in the center of convergence x equals c, so if you think about what's happening in this expression here, so we have a0 plus a1, and if we plug in c, at c, we can say that c minus c to the power 1 plus a2 c minus c to the power 0, to the power 2, plus dot, 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 dot. And we can see right away that what's happening here in all the power terms is that's going to be equal to 0. So what ends up happening is everything collapses here. So we end up with plus 0, plus 0, plus dot, 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 dot. And what we end up with is we know that at c, if we evaluate this function at c, we get a. And that just tells us the first coefficient. Well, that's nice. We know the first a term of that series. Uh, what else do we know? Well, what happens if we take a derivative? So if we take a derivative, that a term differentiates to 0. And the a1 term, we end up with a1. So we're going to do 1. Our power 1 is going to come down. I just need a different color here. Just going to keep the coloring a little bit consistent. So we end up with 1 times a1. X minus c becomes power 0, so that just becomes a constant, plus a2 to a2 x minus c to the power 1, plus this becomes 3a3 x minus c to the power of 2, plus dot, 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 dot. Okay, so what ends up happening is we're applying the power rule to every single term, and so each coefficient gets multiplied by its power. Now, if we evaluate this at c again, notice that we end up, all those power terms ends up equaling 0, and what we end up finding out then is that at the f prime at c allows us to calculate a1. So this is equal to a1. So now we have a0. We figured out what a0 is. We figured out what a1 is. If we take another derivative, well, the next derivative, we're going to end up with the a1 term now differentiates to 0. And if we differentiate that a2 term, we're going to end up with 1 times 2 times a2. So again, just so that you can track what's going on here, this term is differentiating that. And previously, in the previous step, that term differentiated to that term differentiated to that, etc. So we have that term worked out, plus, and that becomes the power 0 because of the power rule, plus, and then we're going to end up with 2 times 3a3 x minus c to the power 1 plus, and this next one will be the next term. Now, as previous, now all those x minus c terms, if we evaluate it at the center c, all those power terms again turn to 0. And what ends up happening again is we end up being left with just 2 times, and I'm maybe just going to keep that 1 times 2 times a2. So what we now know is that if we evaluate the second derivative at c, we have the coefficient a2 times 2, or more specifically, a2 times 1 times 2. And if we continue repeating this, so if I do it for the next term, this constant term cancels out. I differentiate again. This ends up being 1 times 2 times 3 times a3, and that term, the power term, differentiates to 0, so we just end up with a constant. That term ends up being our constant, plus we're going to end up with 2 times 3 times 4 from the previous one for a4 when it differentiates, and now we end up with x minus c. That one's going to be the power 1, and that one came from the previous term. That came from the quadratic term to look like that. Okay? And again, if we evaluate that term at c, at the center, all those power terms, all the x power terms turn to 0, and all we're going to be left with again is going to be this portion here, which is our constant, and that allows us then to gives us an expression at the very least for a3. So now essentially, if we keep differentiating, we're going to be able to work out the values of a0, a1, a2, a3, and again, a4 would look like this. It's going to end up, we differentiate again, 1 times 2 times 3 times 4, okay, because that term comes from here. When we differentiate, we end up with the coefficient a4, the power 1 differentiates to 0, and then, the previous term would have been 2 times 3 times 4 times 5, because it started out as an original 5th degree term in the f of x function. So that one would have been looking like this, a5, oh, I forgot my 5 in here. That has an a5 attached to it, and that would have been this term here. It started off as a power 5 part of that function, but as we differentiate, we're going to get all those coefficients with a5, and you can see that the next time we differentiate that, we're going to lose that x minus c term, plus dot 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 dot, plus dot dot. Okay, but if we evaluate at the center c, again, you can see everything, all those c terms disappear, okay, because all those x minus c's become 0, so we're left with 1 times 2 times 3 times 4 times a4. So now we're able to calculate, using the fourth derivative, we will be able to calculate the coefficient a4. And we can do this repeatedly. Now notice that what's happening, apart from the a4, we have this part here, and we're just going to make that into 4 factorial instead. We're going to make that into 3 factorial. We're going to make that into 2 factorial. This is actually 1 factorial in there. And we can see that we can now generalize this. We're going to end up with, for the nth term, we're going to end up with n factorial. That's the multiplying part. And we're going to end up with a to the power n, evaluated at 0. That becomes, all the other terms have x minus c terms to it, so it becomes 0 plus 0 plus 0, etc. So this is then our generalization. We can see then that we can find out some information about our series by looking at the derivatives, and by doing that, we have expressions for a0, a1, a2, and we can come up with every single a term in that series. Well, what does that tell us about the A term in general then of our power series? Well, we could take this nth expression and we can just solve for an. So that means then if I solve for an, for every an term in this power series, and in fact any power series, every an term can be worked out by the nth derivative evaluated at the center C divided by n factorial. And so this, we've now kind of shown that we can find every single an term of any series, not just this particular one, which, well, we didn't really know what it was anyways, but this will find out the an for any single power series, because as we change the an of this original function, we are getting different of this original function here. We are getting different power series that represent different functions.